So we're talking about having to make sums of lots of numbers. We're adding many, many, many things together here. And notationally speaking, that can be a real bother. So mathematicians have come up with a way to represent this as a sort of shorthand. Surprise. Anyway, we refer to this as sigma notation. It's going to feature the Greek letter sigma, in case you're wondering. So in general, you would see something written like that. So you've got some index k running from 1 up to n. You may notice some similarities with the way we talk about limits in dealing with definite integrals. That's not entirely an accident. Again, this is the Greek letter sigma. That's not an E. It's the Greek S. I'm not Greek. Don't blame me. Anyway, and then we have some expression that should be a K, not an N. My fault. Like that. And this is just shorthand to represent that we're adding up some stuff in a particular pattern. So this looks like a sub 1 plus a sub 2 plus, you get the idea, up until we get to that final index. So we're always stepping in, integer, things. Don't worry about summations with fractions, like, in the index or anything. A1, A2, A3, up to n. So, for instance, we could have something like this. So the summation as k goes from 1 to 4 of 1 over the quantity k plus 1. So that's the same thing as I start from 1, feed 1 in here, 1 plus 1 is 2, so I get 1 half. I do the same thing with 2, 2 plus 1 is 3. Okay, and we can add those together and get a value for what we call the sum of this thing. This one, it's not really saving us all that much. We're only adding up 4 terms. The catch is, what if we got 40 terms or 400 terms? Having to write down all of that stuff in the chain is, a pain, right? So this gives us a way to shorthand that. Moreover, it turns out, again, one of those mini boffins died to bring you this information kind of thing. There are formulas for how you can crank out particular sums. You'll find that in the handout labeled Riemann sums in Moodle. I promise, I am going to tell you what a Riemann sum is before this is all said and done, but patience. But before we do that, let's take a look at invoking some of those formulas. So take a moment while I'm erasing the board here and grab out that handout, have the PDF sitting around, you get the idea. So suppose we were tasked with working out a summation like this. So we're going from 1 to 100. Something like this guy right here. 3k minus 7. And we got to sum that thing up for all integer values of k from 1 up to and through 100. We all have more entertaining things to do than just keep executing that command over and over again and then adding them up, right? So that's where those summation formulas on the handout come in really handy. So I'm going to be a little pedantic here. So technically, sums do the same kinds of things you're used to seeing. We can break them up across addition and subtraction. We can pull constants out front of them. Anyway, so we can do that. Then we can pull the 3 out front, because I didn't think to do it beforehand. So we got that guy there. Now, the handout has a formula for what to do if we're adding up a bunch of k's, what to do if we're adding up a bunch of the same number over and over again. Technically, you probably could have worked that one out anyway, right? All right. So now, our formula for adding up k's is n times n plus 1 divided by 2. So my n in this instance is whatever's sitting in the top of the summation. That's 100. So 100 times 101 divided by 2. Back here, for a constant, it's just the constant times n. Again, hopefully you didn't need a formula explicitly for that. But, so that works out. Pounding out the arithmetic here. I like doing this in stages because it's easier to track where something might have gone wrong. I got 15,150 for this piece. Spoilers, 7 times 100 is 700. Then I do the subtraction. I get 14,450. So, yeah, there were a few steps of algebra through here, and we had to call in some special formulas, but it was a whole lot faster than me methodically going from 1 to 100 and pounding out all those calculations, right? I hope. So, we've got one example of the books. Let's take a look at that one that's a little more involved. Okay. We'll cut down the scope this time. So we'll just go from 1 to 40 instead of from 1 all the way up to 100. But this time around, we'll have a product in there. 2k squared minus 1 times k plus 1. So we don't have a product rule. We're going to have to do some algebra. We got to bust out the FOIL algorithm. We need to expand that thing. So if I'm playing my cards right, and I really hope I am, that's what we get. 2k cubed plus 2k squared minus k minus 1. So now we can break this thing apart using the same, algebra, monkey business, the linearity properties. This breaks up across sums. The 2's can individually hop out front. I'm going to hop over that and then call in the individual summation formulas. So for a k cubed, it's n squared times n plus 1 quantity squared over 4. So I have 40 squared, whoops, got ahead of myself there, 41 squared over 4. The formula for k squared, that's the tricky one to remember. Every now and again I catch myself and I have to go back and look at it and make sure I remember it. So for k squared, we get n times n plus 1 times 2n plus 1. So for an n value of 40, that gives me 40 times 41. 2 times 40 is 80. Then we add the 1. We get an 81 up there. And the whole thing is divided by 6. So the k formula we've already used. So we have 40 times 41 divided by 2. Multiplication dot might be a little tough to see. I promise it's there. And then minus 1, we got 40 of those. That's just negative 40. So minus 40 hanging around the back. Be careful with that. It's really easy for students to overlook this, and they'll either just write minus 1, or they'll, if there's a constant there, they may just remember the 40 here. It won't hurt. But, be careful with that. Remember, it is this constant times whatever the n is for your summation. Okay. So now, when I do my arithmetic, I get 1,344,800. That just rolls off the tongue. This guy here, when I worked it out, I got plus 44,280. This one, not too tough to work out. You could get it without a calculator if you were really pressed. And then I'll write out the minus 40 in the back. So once I combine all these, I get 1,388,220. So, okay. We got that? Hopefully we got that. All right. So that's sigma notation and the summation formulas. Why are we bringing these up? Well, we already saw over the last couple of videos, in order to work out these definite integrals, we're kind of invoking summations in some sense. And we mentioned we're going to have to keep breaking those little rectangles up thinner and thinner and thinner and thinner, and so we have more and more and more of them. So as it turns out, those summations, as we have been writing them, we can condense them using this sigma notation. So what it ends up looking like is a sum, as k goes from 1 to some n. We had one example where it was 4, one where it was 5. We're leaving it unspecified for now. In each instance, we were evaluating some function at a specific point. So we'd have x sub k or c sub k, whatever you want to call it. And then we were multiplying the result of that by this common delta x width thing that we had floating around. So this is an example of what we would call a Riemann sum. So everything we were doing in those previous examples were examples of what we call Riemann sums for the functions in question over the intervals that we were dealing with. So for the record, Riemann was a guy's name, Bernard Riemann, a really important mathematician in the 19th century, died before his time. He has sort of like a Jimi Hendrix thing going on. Except, well, never mind. Just go with that. So we need to work with these things, but we saw we were kind of taking more and more and more of them. So it looked like we were doing something like this, because we were basically letting the number of rectangles we had run off to infinity and beyond. So, yeah, now it gets a little technical.